Hello, welcome to the short lectures in physics. The topic for discussion in this session is refraction of light. It's known that light travels in straight line paths in any homogeneous or uniform medium. When it passes through two or more different media, then the direction of light path changes depending upon the angle at which enters the boundary between the two media. When the path enters at 0 degrees to the uh, boundary of the two media, then the path uh, change do not occur. That means it goes in straight line path as the original path. But if the ray enters at an some angle, then the path deviates from its original direction. This process of bending of light as it passes from one medium to other medium at the point of incidence at the boundary is known as refraction of light. The media can be either denser or thinner, that is rarer types. So it travels faster in medium like air, which is a rarer medium, than in a denser medium like glass. The refraction of light occurs due to the differences in the speed of light in different media when they pass through such denser or rarer mediums. When light travels from a rarer medium to a denser medium, the light ray bends towards the normal. That means if you draw a normal at the boundary surface, at the point of light ray falling, the light ray bends towards the normal when it travels from rarer to denser medium. It bends away from the normal if it travels from a denser medium to rarer, that is in the reverse direction. You can see this in this figure clearly. So the air is the uh, rarer medium and glass is the denser medium. So the incident beam is coming from a rarer medium and entering into a denser medium at an angle of incidence I. It then, because it entered into a denser medium, the refracted beam deviates from its original path and bends towards the normal with an angle of refraction R. Then it continues in the straight path in the denser medium till it crosses the boundary between the denser to rarer medium. When it crosses the denser medium to rarer medium, it again deviates its path from the refracted beam direction and then leaves the denser medium as an emergent beam with an angle of emergence which is equal to angle of incidence initial angle of incidence. If you observe these paths clearly, you can note that the angle of incidence is more than the angle of refraction as the light ray entering the denser medium from a rarer medium. Similarly, the angle of incidence R is less than the angle of emergence I as light ray leaves from the denser medium to rarer medium. Also, we can note that the incident ray at the rarer denser medium boundary and the emergent ray at the denser rarer medium boundary are parallel to each other because angle of incidence and angle of emergence are same. They both remain parallel. However, there exists some lateral shift. Well, that means the incident ray beam and emergent ray beam are slightly shifted through some distance laterally. This is called lateral shift between the straight line paths of both incident and emergent beams. So some of the characteristics of refraction of light: the velocity and wavelength of light depends on the media through which it travels. However, its frequency remains same. At the boundary of surface of two media, the light gets partly reflected back, partly transmitted, and partly gets absorbed in the media material. After reflection and absorption, the rest of the light leaves the media and emerges out. So as a result, the intensity of the refracted beam will be less than that of the incident beam. And one more characteristic is the incident ray, the refracted ray and the normal at any point of incidence all lie in the same plane. The ratio between the sine of the angle of incidence, that is sin A, and the sine of angle of refraction, that is sin R, is a constant. That is sin I by sin R ratio remains constant for a given combination of two media like glass and air. This constant is known as refractive index of the medium in which the refraction is taking place with reference to the medium through which incident ray travels, say medium 1. And this is represented as 1 mu 2. 1 mu 2 means it is the refractive index of medium 2 with reference to medium 1. In general, if the reference medium is A, then it is indicated as mu 2. Thus, sin A by sin R is equal to the refractive index indicated as mu. This equation is known as Snell's law. This holds good for all angles of incidence. If there is mu1 with reference to A and that of second medium mu2, that is mu2 with reference to A, then the refractive index of medium 2 with reference to medium 1 can be represented as mu1 2 is equal to mu2 by mu1, that is sin A by sin R. Thus, mu1 sin I is equal to mu2 sin R. Mu1 is the refractive index of the medium in which the light is entering the boundary, and mu2 is the refractive index of the medium in which refraction took place. So, mu1 sin I is equal to mu2 sin R, or this can be represented as mu sin I for any medium is constant. Here, you can also note that in reflection, the angle of incidence I is equal to angle of reflection R, but in refraction, the product of mu1 into sin I is equal to mu2 into sin R. Also, the refractive index is a measure of the velocity of light in that medium. A medium with higher refractive index is known as optically denser, and a medium with smaller value is optically rarer. The refractive index in terms of velocity of light can be defined as the ratio between the velocity of light in vacuum divided by the velocity of light in the particular medium V. That is, mu is equal to C by V. It may be noted that velocity of light in a medium is the ratio of velocity of light in vacuum with its refractive index. That is, V is equal to C by mu. C is the velocity of light in vacuum by refractive index of the medium. In general, the refractive index values for different glass materials used in optical instruments ranges from 1.46 to 1.96. However, for a diamond, its value is 2.47. Absolute value of refractive index of a medium cannot be less than 1 unity. This is because the velocity of light in any medium is less than that in vacuum. However, its value can be less than 1 for a rarer medium like water with reference to denser medium. Similarly, its value can be more than 1 for a denser medium with reference to a rarer medium. Maximum value is 2.47 for diamond. Now we can see another characteristic of refraction, that is principle of reversibility of light. That means light as it travels retrace back its original path if it happen to be reflected back through any means. So in this slide you can see there is a glass slab filled with water, and a light ray is entering the boundary between air and water medium at the boundary surface at the point O, making an angle of incidence I. And in the water medium it refracts through an angle of refraction R. Suppose at the bottom of the water tank we keep a mirror perpendicular to the direction of the refracted beam, that is OQ, ray OQ in the picture. Then the refracted beam reflects back from the mirror M and then retraces its path along QO, and then it refracts along OP. Then the refracted beam retraces its path back to point P. Now the angle of refraction R becomes the angle of incidence and the I becomes the angle of refraction. This is known as the principle of reversibility of light. So from this we can understand that for light ray entering air to water, mu AW is equal to sin A by sin R, and for light ray entering water to air, mu AW, that is sin R by sin A. Thus we can observe that they are the one is reciprocal of the other. That is, refractive index of water with reference to air is nothing but inverse of refractive index of air with reference to water. That is, A mu W is equal to 1 by W mu A, or W mu A is equal to 1 by A mu W. This is another useful expression obtained from principle of reversibility. Now, refraction through a rectangular glass slab, that is, consider a parallel-sided rectangular shaped glass slab through which the refraction properties are studied. Here, PQ is the incident beam falling at point Q at the boundary between air medium and glass medium, making an angle of incidence I. The ray refracts through the glass slab as ray QR and leaves the glass slab as RS. The angle of refraction in the glass medium is R, and the angle of emergence at the boundary of glass to A is again I. Note that the incident ray PQ and the emergent ray RS are parallel to each other because angles are same as I. However, the refracted beam is refracted through an angle that is less than the angle of incidence by an angle theta as shown in the slide. The theta is the angular difference between I and R. So if you extend the incident ray PQ and then drop a perpendicular from the point of emergence R, the perpendicular is RT. So the RT is a measure of the lateral displacement of the incident beam and the emergent beam. So the lateral shift is the deviation observed in the original path of light ray PQ as it emerges as emergent ray RS. So in the triangle RQT, sin theta is equal to RT by QR. RT is, let RT be small d, the lateral displacement, d by QR. And in triangle QUR, cos R is equal to QU by QR. That is, QU is the thickness of the glass slab, let it be T, so T by QR. Thus, QR becomes T by cos R. Thus, the lateral displacement d is equal to T times sin theta by cos R. That is equal to T times, theta is nothing but sin of I minus R. Theta is the difference between I and R, I minus R. So, d is equal to T into sin I minus R by cos R. This is the expression for lateral shift of the emergent beam from the incident beam. That lateral shift d increases with increase in thickness because d is proportional to t, and the angle of incidence I with increase in refractive index of the slab. It will be maximum when angle of incidence is 90 degrees. Another characteristic is apparent depth of an object kept at the bottom of a water tub. In this slide you can see there is a object R kept at the bottom of the water tank, and a person is observing the object from point P. The light ray travels RQ and then refracts as QP. There is one more ray going straight, that is along the normal, like normal incidence, along the line RO. If you extend the emergent beam QP back onto the normal line OR, then it touches at point S. The point S is the place where the object appears to an observer observing the object from point P. So the angle of incidence is I and the angle of refraction is R as shown in this slide. The RS represents the apparent rise of the object at the bottom, and Ts represents the apparent depth. Then, to a person looking from point O at the object appears to be at point S, though it is at point R, still lower depth. Let h is equal to Ts be the apparent depth of the object as viewed with the observer, and capital H Tr the actual depth. Then the refractive index of air with reference to water is sin A by sin R. Because the light ray is traveling from water to air medium, we are taking the refractive index of air with reference to water. So W mu A is equal to sin A by sin R, that is equal to sin A is equal to Qt by Qr, sin R is equal to Qt by Qs. So sin A by sin R becomes Qs by Qr. When the object is viewed normally from point O directly downwards, the points Q and T appear to be very close. Then Qs is equal to Ts, that is equal to small h, and Qr is equal to Tr, that is equal to capital H. Capital H is the depth of the water level, and small h is the apparent depth of the object. Thus, W mu A is equal to small h by capital H. Or inverse of that is refractive index of water with reference to air is equal to capital H by small h. So the apparent depth h is equal to real depth capital H by refractive index of water medium. Thus, depending on the refractive index value of the medium, the apparent depth can be obtained from the expression using the real depth of the water tank. That is, apparent depth small h is equal to capital H by refractive index of the medium mu W. Apparent normal shift is the height through which object appears to be raised in a denser medium when viewed vertically down from a rarer medium. So apparent normal shift D is equal to real depth minus apparent depth, that is capital H minus small h, that is equal to H capital H into 1 minus small h by capital H, that is equal to capital H, or that is real depth, into 1 minus 1 by refractive index of medium, that is capital H into 1 minus 1 by uw. So the apparent depth depends only on the depth of the water level depth and the refractive index of the denser medium. So these are the apparent depth of the object can be estimated. Now consider, instead of one medium, there are 2 or 3 or 4 mediums, multimedia. Like in the slide, we have shown 3 mediums with refractive indices mu1, mu2, mu3, and having different depths T1, T2, T3. And suppose an object is kept at the bottom of the slab, different media combination. Because of the refraction phenomena, when a person looks at the object placed at the bottom of the medium 3, it also appears to be raised through some height, say small d. That is the apparent position of the object indicated in the slide. So due to multiple refractions through medium 1, medium 2, medium 3, etc., the light ray coming from object at the bottom leaves the boundary between medium 3 and medium 2, then leaves medium 2 boundary between medium 2 and medium 1, then it leaves the medium 1 and then enter into the air. So many multiple refractions occur in all the 3 media. As a result, the object appears at a lesser depth than the actual depth. Due to refraction, medium 1 in the object image is D1 is given by T1, that is thickness of the glass medium 1 into 1 minus 1 by mu1, refractive index of medium 1. Similarly, due to refraction in medium 2, the shift D2 is equal to T2 into 1 minus 1 by mu2. Mu2 is the refractive index of medium 2. Similarly, for the medium 3, the shift T3 is equal to T3 into 1 minus 1 by mu3. So then the net shift can be obtained as D is equal to D1 plus D2 plus D3, that is equal to T1 plus T2 plus T3 minus T1 by mu1 plus T2 by mu2 plus T3 by mu3. Multiple refraction of light coming from distant objects like planet and stars also undergoes multiple refractions, hence this is known as atmospheric refraction. Because of this, the sun appears few minutes before its sunrise, about 4 minutes, and appears for more time even after the sunset. So the day time appears to be longer than actual sunrise sunset based time calculation. Due to atmospheric refraction, the sun appears to be flat instead of round shape during sunrise sunset times also. The stars also appear at higher altitudes than their actual heights altitudes, and they appear twinkling because of the fluctuations in their brightness as their apparent altitudes keep changing due to temperature and convectional currents effects in the atmospheric zones. Consider a parallel-sided rectangular water tank placed over another solid glass slab as shown. Let a ray of light OP enters this compound system at the point P with an angle of incidence I1. As it enters the water tank, it refracts through an angle R1 and travels through the water medium as ray PQ. At the point Q, it meets the boundary between the glass and air mediums again. Again, it refracts at an angle of incidence R1 and refracts through the air medium at an angle of emergence I1 and it proceeds as ray RS. So the angles of refraction in water and glass mediums are R1 and R2 respectively. Angle of incidence at air water boundary and angle of emergence at glass air boundary are equal as E1, I1. Thus the incident ray OP and emergent ray QP will be parallel, however with some lateral shift. All the angles are measured, of course, with reference to the normals drawn AB at point P, CD at point Q, and EF at point R. According to Snell's law, the refractive index of water with reference to A, that is A mu W is equal to sin I1 by sin R1. Refractive index of glass with reference to water is given as sin R1 by sin R2, and the refractive index of air with reference to glass is given as sin R2 by sin I1. If you multiply all these three refractive index equations, you get mu of water with reference to air into mu of glass with reference to water into mu of air with reference to glass. If you take this product, the product becomes 1 unit. Since the product is 1, so if you know the refractive index of two media, then you can find out the refractive index of the third medium. That is, if you know the refractive index of water and glass with reference to air, then we can estimate the refractive index of glass with reference to water, or the refractive index of water with reference to glass can be estimated. These are some of the salient points with reference to refraction of light and different conditions and the lateral shifts and the apparent depth calculations in two or more media conservations. Hope this finds useful to you. See you in the next session. Till then, bye.